Good evening. Good evening. Today our speaker is Priyanka Jalan. She is a PhD in Delhi. After 1 year experience, she came to Poland 2022. Work in a theoretical center of physics with Maciej Bilicki. And she talked us about the FLAME project. The floor is yours.
Thank you so much. So, first of all, before I even start with my talk, I would like to thank Marush and Liana for giving me this opportunity to present my recent work. As Marush said, that I'm a postdoc with Maciej. However, today I'm going to talk about a project which I started when I completed my PhD. And the topic is FLAME, which is divided into basically two parts of the title. The first part is the Lyman-alpha absorption line. Do we have a pointer?
Just the class one.
Okay.
Yes.
Okay. So the first part is the Lyman-alpha absorption line. As the name says, the Lyman-alpha, which is a transition in hydrogen atoms from ground state to the first excited state. I'm going to talk about this transition in context of intergalactic medium, which you can see in the middle panel in the first figure. It comes from the cloud or in the galactic medium, which is present between the quasar and the observer. And in the side panel, I'm showing one such absorption line. And the second part is using machine learning to fit these absorption lines. So here I'm showing an example of a convolutional neural network, which is a type of machine learning. And in this image, I'm showing how to identify whether this image is of a dog or not. So that's the title, and that's going to be the flow of the talk as well. I'm going to talk about how we fit these Lyman-alpha absorption line using machine learning. So I'm going to talk the details about individual topic and then what we have done regarding the subject and how this was important at that time. So to start with the Lyman-alpha, let's start from the very beginning when the Big Bang happened, and we had a hot, dense universe. And after creating of this Big Bang, after that, we had a very exponential expansion of the universe known as the inflation. As you can see, I hope you can see the pointer. So that's the period of inflation. Because of this inflation, the universe cooled down, and hence the charged particles could combine, giving this epoch of recombination. Oh, thank you so much. Okay, great. So we have this epoch of recombination or the cosmic microwave background, after which the photons could actually move freely and we could see them today. This happened at redshift around 1100. This was followed by dark ages because we do not have any structure here which emits light. It's all composed of like neutral hydrogen. This followed by at redshift around 20. So before I go to the redshift part, I know it might be very obvious for some people, but redshift is basically a measurement of distance. It's a proxy for distance. So if I'm saying higher redshift, that means at higher distance. So 1100 means much higher than at the redshift of 20, and it does not scale linearly. So how we measure it, I'll come to the later slides. So then we have at redshift 20 the first stars or the first structure formation. These structures after forming, so they form like galaxies and quasars, and these structures are formed around redshift of 20. Once these structures starts to form, they also starts to radiate ionizing photons, ionizing the region which is in the vicinity of the object. So like they would ionize the proximate region. These regions, so when the structure formation actually started, it was not 100% efficient. So not all the material which was present in the universe was actually utilized to form these structures. And therefore, some of the material remained in the medium, and that's the medium called intergalactic medium, like the medium which is present in between the galaxies. And you can see that the structure starts to form and they starts to ionize their nearby region. So when these bubbles starts to overlap, these ionized region of proximity starts to overlap, this starts to ionize the intergalactic medium, and this is known as the epoch of reionization. This is not like one epoch, I mean, it ranges. So it ranges from 7 to around 5. Then we have the fully ionized intergalactic medium. And today also we see this ionized intergalactic medium, which can be observed by other telescopes like UV and X-ray. So just to summarize or basically say one line about this slide is that we have something called intergalactic medium, which is present between the galaxies. And we can study about this intergalactic medium using quasars. So what are quasars is I'm going to talk about next. So if we see a quasars are very high luminous sources, and they are a subclass of active galactic nuclei, or in short, AGN. So the name says active. So there is something which is active, and that is a supermassive black hole. And the supermassive black hole starts to accrete and then radiate out. And I'm showing two images of two normal galaxies here, where you can see the structure, you can see the bulb, you can see the spiral arms here. And in the lower panel, I'm showing two examples of an active galaxy. And you can see that the central part is actually outshining the entire galaxy. So they are very luminous, and if you see the intensity versus frequency or wavelength, they emit in all the wavelengths starting from radio to X-ray. So because they're very luminous and they can be seen at very high distances or at various redshifts, it's very useful to study about the intergalactic medium based on their absorption spectrum. So if you see here the quasar, so this is just an artistic image, so it's a very simple image of that. So because of the expansion of the universe, all the wavelengths which are emitted by the quasars are redshifted by a factor of 1 plus z. So lambda emitted turns to be lambda emitted times 1 plus z. Once this quasar emits any radiation below the wavelength of 1216 angstrom, which is the wavelength corresponding to the Lyman-alpha, it is redshifted, and it is redshifted in such a way that dependent on the cloud or the intergalactic medium cloud absorber, it is redshifted and is seen as Lyman-alpha. So all the wavelengths that are blueward of the Lyman-alpha in the quasar emission would be passing through the intergalactic medium, and dependent on the redshift of the cloud, we can see the absorption lines. Now this, as I said, the redshift depends on what is observed, what is res. Then this absorption also depends on the column density and the Doppler width of these clouds. Here I'm showing one example video which I've taken from Janssen page. When the quasar continuum passes through the intergalactic medium, you can see that this is the Lyman-alpha emission line, and blueward of it, you can see all the Lyman-alpha transition or the absorption lines here. So this is the 1216 angstrom line, which is shifted because of the quasar redshift. And you can see the absorption lines also shifted, but you can also see the Lyman beta transitions here and the Lyman gamma transitions here. So this is just one example. Maybe I'll play it one more time so that you can see. So you can see here that in the rest wavelength, it's 1216 angstrom, and when it passes, if the quasar is present at higher redshift, it would shift dependent on the redshift of the quasar, and blueward of it, we would see these transitions. Okay, so what we have here is something called the Lyman-alpha forest, and it's easy to guess why it's called forest because so many lines are present there, and it gives an impression of a forest. And not just the Lyman-alpha forest, not about just the neutral hydrogen present in the intergalactic medium. The quasar spectrum are also very important for sources like very faint galaxies, which we would not have seen otherwise. So we would not be seeing them from the current telescopes. But because they are present as an absorption in the quasar spectrum, we can see them as a damped Lyman-alpha system in the quasar spectrum. So this region is particularly interesting because it has mostly Lyman-alpha transitions. To understand what I'm saying by just Lyman-alpha transition is the fact that if you see cloud 1 and cloud 2 here, the Lyman-alpha absorption of the cloud 1 would be at this position, but the Lyman beta absorption from the same cloud would be happening in this place, which would overlap with the Lyman alpha absorption of cloud 2. And therefore, whatever absorption we see bluewards of the Lyman beta is actually like a contamination. There could be Lyman beta and Lyman alpha absorption overlapping from different clouds, However, in this region, what we have is just the Lyman-alpha absorption. Okay. So if we zoom in, or basically see a high resolution spectrum of such quasar spectrum, we see that there are various profiles. We see that these lines are not just like noise lines, but rather they have a profile. And this profile can be well understood via Voigt profile, which is a convolution of Gaussian and Lorentzian profile. So this two convolution which I'm talking about, the first part comes from the Lorentzian profile, and it's caused because of the Heisenberg uncertainty principle. So we know by the Heisenberg uncertainty principle that there is a fundamental limit to which we can measure the energy and time of a quantum state. And therefore, the frequency of the emitted photon is not mu naught, but rather a profile which is like a Lorentzian profile, which you can see here. The other part, which I was talking about, the convolution part of the Gaussian, is coming from the thermal broadening, which happens because of the random motion of the particles. So we see here that some of the particles are low shifted, so that means they are moving towards you, and some of the particles are moving away from you and hence red shifted. And therefore, what we see is like a distribution, which is a Maxwellian distribution. But also the cloud itself can be in a turbulent motion. So therefore, there is also a turbulent velocity. So this results in a profile. If we convert these two profiles, we get Voigt profile. And you can see from this that in the central part, it's mostly dominated by the Gaussian, whereas at the very edges, it is mostly dominated by the Lorentzian profile. There is one more convolution that happens, but it's about an observational effect rather than the natural one. And I'll talk about this later when I talk about the real data, real observed spectrum. So just a recap, and also I would, if it's okay, I would like that if there is any question, an immediate question regarding the part which I've already discussed, then you can ask now. Then the recap is that we have intergalactic medium, and then we can study about this intergalactic medium using the quasar spectrum or fitting Voigt profile to these lines. So, any question? Immediate question? Okay. So, okay, now we understand that, okay, we have these Lyman-alpha absorption lines and we can fit them by Voigt profile. But what information do actually these lines provide? They provide information about the column density and the Doppler width. So this B and N, so B is the Doppler width and N is the column density, is actually a space that maps the density and temperature. So the B maps the temperature and the density maps, or the column density maps the density. So here I'm showing an example which I've taken from Janssen's paper. These are not the Lyman-alpha absorption, but rather more optically thick systems. They have column densities of around 19.5. And you can see the data in the black, and you can see the fitting of Voigt profile in red. So once we have this fitting of B and N, as I said, we can map the temperature and density and hence the equation of state. But not only this, we can also measure the column density evolution with redshift if we see this quasar spectrum at various redshifts. And this is what I'm showing here, that at very low redshift, we can see that, so this is the, again, going back to the same thing, this is the Lyman-alpha emission line, this is the redshift 0.4 quasar, and you can see the Lyman-alpha forest here. And you see there are very few lines as compared to what I've shown in the previous slide. It is more similar to what I've shown in the previous slide with this quasar spectrum, which is at redshift 3. And you can see that there are more number of absorption lines present now. So that's the red solid part which you see here is basically the quasar continuum. And the lines that you see here are the absorption lines or the Lyman-alpha absorption lines I'm talking about. But if we go to a very high redshift quasar spectrum near the epoch of reionization, because the intergalactic medium is still very neutral, the continuum is totally absorbed by the neutral hydrogen content, and hence what we have is something called Gunn-Peterson trough. So what we see here is that the number of lines in the number of absorption lines are actually evolving with the redshift, and that's another method or indirect method of studying about the epoch of reionization. Other than this, what you can do with the Lyman-alpha forest study is you can calculate the ionizing background radiation. So when I was talking about the epoch of reionization here, so I said that they starts to overlap. The ionizing bubble starts to overlap. And hence, they create a background of ionizing photons, which is known as the ultraviolet background radiation. And what you can do is, by fitting these Lyman-alpha forest lines, you can calculate this ionization parameter. So this intergalactic medium is in photoionization equilibrium, that is with the quasars and galaxies. And what you have is here the ionization equilibrium equation. By fitting these lines, you can get the baryon density, the temperature, and hence you can just rearrange this equation and calculate the ionization of the ultraviolet background radiation. But there is another method of calculating such ionization background radiation is by using the emissivity from the quasars or galaxies. Because this ultraviolet background radiation is created or generated by the quasars and galaxies. What we can do is we can calculate what is the escape fraction of those ionizing photons that got out of the galaxies or quasars. And then based on that escape fraction of those ionizing photons, we have the distribution here with the redshift. So this is just redshift here. And you see that at very low redshift, we have the dominance by the quasars. However, at very high redshift, we have the dominance by the galaxies. And this generates the ultraviolet background radiation here. Now, suppose the ionizing radiation or the ultraviolet background, UVB in short, measured by these two methods, so measured by the emissivity process and measured by the Lyman-alpha forest, are inconsistent. So we have, say, the ionization fraction measured by the emissivity much smaller than what we have from Lyman-alpha forest. That means that we are missing some of the sources which are contributing to the ionizing photons. And therefore, it's easier to detect knowing once what we are actually missing. So now we have this information that we can study this by intergalactic medium, by Lyman-alpha forest study, and we can study them by fitting the Voigt profile. But the question is, why do we need CNN for that? Why do we need machine learning for that? I mean, I think we can already see here that from even one quasar at very low redshift, fitting individual lines would be really painful. And if we go to higher redshift, we can see that there are so many Lyman-alpha absorption lines, even in one spectrum. And if we consider about what we have like millions of quasar data available now, then it's almost impossible to fit them manually, but also by semi-automated codes, it's computationally expensive. So it's, again, very tiring, and therefore we need machine learning. So I'm going to talk about a technical part for it. Again, I would ask if there is any immediate question before I go to the technical part of machine learning. Okay, all clear. So what is machine learning? In a very analogous method, what I understood from machine learning is as if you're teaching a kid. Like if you teach a kid and you show them examples of say car and truck, and you ask them multiple times. So you show that first of all the data, the car and trucks multiple times. So you train them on given this training data set. And then you ask them questions, okay? And you ask them whether this is a car or truck. And if they suppose answer it correctly, you would say, oh, it's a good answer. But if they answer it wrong, then you give them the feedback that no, it's a wrong answer. So this is an iterative process, how you train and test. And similar thing is going on with the machine learning. Machine learning can be actually there are various kinds of machine learning, but in a broad sense, there are two types. The first is an unsupervised machine learning, where you do not basically label them as car or truck. You have those data points. You have some properties which are similar or dissimilar in the points. So like in this case, if there's an unsupervised machine learning, you have the data which is unlabeled. And therefore, it clusters around. It's very similar to what we have in k-nearest neighbors or in clustering, any clustering method. And the properties of and the balls which have similar properties would cluster at same place, but the properties the spheres which have vastly different properties would be very far away from it. I would be happy to talk about unsupervised machine learning in more detail if we have time after this. On the other hand, for this project, I'm going to talk only about supervised machine learning, which is the data which is labeled. As I said, it has been labeled as color. In this case, it has been labeled as red and green. And then you can do both classification. You can have this kind of classification algorithm, or you can do a regression analysis based on this machine learning. If I have to talk about in very broad sense, it would be 4 parts. The first part, as I said, is the data set, which is divided into, first of all, the training data set, and the other part is used as testing or validation data set. As I said, you train with the given data, but you also test it, which has a true label given. So the data itself is totally labeled. So you have all the cars and trucks in this data set, which are labeled, and you then divide them as training and validation data set. Now, this training data set has all this data, again, I said, has labels, but for this training data set is what we input in the model. Whereas the validation and testing data set, we test the model how it works. So we know the true labels for this data set as well, but we do not put the labels, we just compare it. So whatever results you see mostly in machine learning papers are given for this test data set. When this input sample is used, this is sent into this building model, which I will talk in detail about later. But you have this building network model. And the idea here is that once you have trained the model, it does it iteratively. And ultimately, your goal is to reduce this loss. So like every time you teach the kid, you have to reduce the times the kid is answering a wrong answer. So you want to minimize that. So it's similar to that. So loss function is minimized. And you use a technique called optimization. And this process is iterative till you're satisfied with the result. So coming to the building network model, which is a CNN in this case, a convolutional neural network, you have some layers. So suppose let's talk about an image, which is an RGB image here. The first operation is a convolutional operation, which is then followed by an activation function, which is then followed by a pooling layer. So this is a convolutional block together, as you can see here. So this is the convolutional block here, where these are the convolutional layers. What convolutional neural network, as I said, again, it's because of the convolution. And if suppose you have an image like this, you choose a kernel, and based on your kernel and your input image, you have the output. And this happens for all the image pixels. So you have all this continues for all the image pixels. And the idea of convolution is to extract an important parameter of those images. As I said here, sorry. So this happens continuously, iteratively, basically. And there are some of the parameters which are used. So like suppose in this case, what should be the kernel size? How this iteration should go on? How this kernel should be convolving? How much should be the strides of those convolutions? These are all hyperparameters. And this is the main thing in machine learning, that you have to change the hyperparameters according to your science code. Then the second part comes is that once you have this activation or this feature map, it passes through an activation function, which is very similar to what we have in biology, of where you have a neuron and you have the inputs and you have then an output, and based on what kind of signal is passed, we have an output. Similar thing goes on with the activation function. Activation function decides which of the neuron would be active. And here is what we have as input. They have weights. There is a bias term. And once that is input to an activation function, again, dependent on your science goal, you would have the output. Then we have this activation map after the activation function. We use the pooling layer. Now, pooling is generally used to reduce the image size. So like in this case, suppose after the activation function, we have this as the image. So you remember the last time we had the image. Now it's reduced because it has convolved. And now we have this image size. Dependent on what kind of pooling you choose, you can choose either max pooling or you can choose average pooling. So suppose you choose a max pooling, then again, dependent on your hyperparameter, which you choose, which kernel size you choose. So suppose in this case, I choose a 2 by 2 matrix. And then in max pooling, I would just choose maximum of this value, while in average pooling, we would have an average value for the same thing. After this, we have, so the convolutional neural network part is now done. Now, this is generally followed by densely connected layers. The name suggests densely. So all the neurons in one layer are connected. All the particles are densely connected in the next layer. In all the okay. And I have seen a very good example of this densely connected layers or deep neural network in Nicholas Copernicus Science Center when I went there. And they also have a similar thing where they use a handwritten number and it's ultimately detected which number is it. So like in this case, a handwritten number is 7 and the output is also 7. Okay. So now we have built the model. We have all the convolutional layers. We have the dense layers. The idea was to reduce the loss function. Now, what you can do is, suppose in this case of classification, you can have models which the loss reduces, and it reduces fine. But you also have to test this, whether this loss function of the validation data set is also reducing. So now say both of them are reducing, but they do not reduce it enough. So that means the model is not fitting the data well. So that is underfitting. What you have to do is in that case, you have to train it for more number of epochs. So the iteration has to be increased. Or maybe you have to increase the number of layers in that case. Another situation could be where your training loss reduces, but your validation loss increases. What that means is that your model is learning good enough for the training data set, but it's not learning, it's not making a generalization learning. It is very specific to what you are learning for the training loss, but it's not making a generalized, right? So it's like overfitting to your data set. So like in this case, it's doing the classification, but again, it's very overfitted. And therefore, you have to be somewhere in between. You do not have to overfit the data, but also not underfit. And one of the hyperparameters to do such thing is known as early stopping criteria, where the loss function of training data set as well as validation loss also reduces. And you have an optimal fitting of the classification problem. And the last part of this machine learning model is the optimization. So you have to optimize how your loss function is reducing, right? Your ultimate goal of reducing the loss function. And you can do this by changing the hyperparameter called learning rate. And if suppose your learning rate is very high, it's something like it's a potential well, like in this case. And if you change the parameters very fast, it would just jump from one place to another and would never go to the minimum. However, if you have a too low learning rate, it would move very slightly or very small to reach the minimum point. However, if you have just the right amount of hyperparameter of learning rate, it would simply go to the minimum point. And this is what people mean by when they talk about convergence or divergence of a model. That your model has to learn, but also to reach, like you cannot take infinite number of time to make the model to learn. And this is where the optimizer comes into the picture. So again, I would stop for a minute, and if there is any question, I would like to take it. Okay, probably not. So let's go back to the problem in hand, and the question was whether we can get the we can fit the absorption line and get the column densities and Doppler width of the absorption line. As I said before, we need a training data set for this, but unfortunately, we do not have such training data set for this Lyman-alpha forest absorption, not enough training data set. So what we did is we simulated such absorption lines given the column densities and the Doppler width. But if you see this simulated data, this doesn't look like what the real data look like, as I showed before. The real data has noise. The real data is convolved with the spectrograph which it is absorbed. So Now coming back to again the convolution part. Here, the convolution is happening because the data itself passes through a spectrograph. And hence what we have the line spread function, which is generally a Gaussian distribution. So when an absorption line passes through the spectrograph, it gets convolved. And hence what we have is not the real such simulated lines, which we are seeing here, but rather a convolved line. In addition, that we also have noise. So this is more realistic. This is more of what is closer to the true absorption lines. So you see here in the brown color, you have the simulated line, which I showed before. And then in the convolved, you can see in the green part here, slightly visible. And then in the red, we have the noise added to each piece. In this project, we have only dealt with low redshift quasar data. And the data which we were testing on had only like 90% of the data were either single or double lines. Of course, as I showed before, there are much more complex data. But for this part, we only considered single and double. So we had single simulated lines, and then we have double absorption lines. You can see individual line in the dash part. And then when they are together, we have this double absorption line. They are overlapping with each other. And the final line looks like in this red part. Okay, now we have the data. Now we have to build the model. Now, in this case, we built two models. The first is to classify whether it's a single or double line. And then we identify the parameters, B and N. Okay, so for single line, it's easy. It's B and N parameters. But for the double lines, we have B and N for individual lines. So B and N parameter for this line, B and N parameter for this line. But also we need to know the separation between these two lines. So this is what the model, the plain model has. It has a classification model. It has a model to get the parameters for single line and the parameters for the double line. Okay, so let's build the classification algorithm. So we input these fluxes, which we have simulated, to a classification model. We train this model. So now this model has been trained. We input the testing data set or the validation data set and compare it with the true labels of this testing data set. And in this case, the labels are number of lines. So either it's 1 or 2. So that's the model which we have given. So we have this true single one line or true double line. We input this to this model. And you can now see the parameters. We have the convolutional layer, we have the max pooling layer, and then we have this two convolutional layers. So the convolution block itself contains two convolutional layers, and then it is followed by our dense layers. And again, the output is number of lines present in the spectrum. Once we do this, we have something called confusion matrix. The confusion matrix here basically tells us how the true versus what the model is predicting. So in this case, the truths are 1 and 2, and the predicted values are 1 and 2 as well. Now, given the true values, the model predicts them as single line 97.5% of the time. However, 2.5% of the time, the model mispredicts them and identifies them as double line. Whereas for the double line, it predicts them as truly as double line 90% of the time, and 10% of the time it misidentifies them as single line. So why this misidentification happens? So here I'm showing an example of this confusion matrix. So from each cell, basically I've taken two examples of the absorption lines. So the true positive, where the single line is identified as single line, as you can see, visually also seems fair single line. But the lines which are identified as double line or misidentified as double line are generally the lines which have low signal to noise ratio. So we found that if the line has a signal to noise ratio less than 10, our model does not perform enough as good as it would perform for high signal to noise ratio. For the cases of double lines predicted as double lines, again, visually evident that they are double lines. But the lines which are misidentified double lines as single lines are generally those lines which are either very close to each other. So the velocity separation between the two lines are very small. So the velocity separation between these two lines are very small. or they are very saturated lines. So if one of the lines is very saturated, so then we do not see them as two separate lines. Once we have identified what is the number of lines in the spectrum, now comes what is the column densities and the Doppler width of these lines. So we have again the same training data set, but now we have to increase the data because what we were finding that it was not performing well, it was underfitting for those cases. And therefore, we have to increase the data set. So we simulated more such data training data sets and again input it to the model, tested, again trained the model and tested for the testing data set. But now the output is column densities, Doppler width, and velocity separation between the two lines if it's a case of two lines. And here are the results for this case. Now, one thing I think that's why I put this image here, is to show that the training and testing data set overlaps in the parameter space. So when I distribute the data, it's important to ensure that your testing data set is actually overlapping with the training data set. There are models which you can use, which are called transfer learning, where you can sort of extrapolate. But in general, we have seen in machine learning that when you extrapolate the data, your predictions can be good or bad. But if it is overlapping with what you are training it with, it generally performs well if you have built the model correctly. So in the upper panel, I'm showing for single line now, the true versus predicted. So the true are the true labels which we have used to generate the simulated data. And the predicted parameters are the predictions from the machine learning. And you can see that the distribution is centered around 0. And what we have here is the 90 percentile value for the column density, which is around 0.33. And we have the true versus true minus predicted for the Doppler broadening, and this is around 6 or 7 kilometers per second. So one thing I forgot to mention about this is that the simulated data, when we make it convolve, we convolve it with the Hubble Space Telescope spectrograph, because as I said, we are going to talk about only low redshift data. And the low redshift data, because the Lyman-alpha forest shift to the ultraviolet regime, it can only be observed with HST. And this is what the pixel size or the velocity resolution of HST is as well. So our predictions are within like one or two pixels of that resolution. You must have seen these kinds of plots in a lot of machine learning paper, which is a true versus predicted plot. We have the black line, which is the 1-to-1 line. And you can see that the spread is near this 1-to-1 line. We have the column density, and here we have the Doppler. In this panel, I'm showing one such example of a single line. Again, it's a simulated data set. So we have the data in this brown color and the prediction of this line by this model in black. And you can see the residual here. So the parameters predicted are also mentioned here. And this is a very low resolution. This is a very low signal to noise. It's not very high. It's 14 point something. But even for, if we go to very high signal to noise ratio data, our model performs well for the single line. Now coming to the double line data, we had two Doppler parameters and two column densities now. So that's why we have two histograms here. And you can see again, they are centered 0, but the spread has sort of increased now for the double line. As you can also see it in the bottom panel that there is a spread now with more spread as compared to what we have the single line. And then you also have the another parameter, which is the velocity separation between the two lines, which is doing a pretty good job here, as you can see in the true versus predicted line. Okay, great. So we have this now for the simulated data set. We tested our model for the simulated data set, but we also need to test it for the real data. As I said, we do not have enough training data set, but there are studies where they have fitted like 80 or 100 quasar spectrum, either by manual fitting or by some semi-automated codes. And you can see one example of such spectrum. So you have these Lyman-alpha absorption lines here in the spectrum of the quasar. And this is a study by Danforth et al. Where they provide a list of around 1,500 such Lyman-alpha absorption systems. And we also fitted these lines by a semi-automated code called Vipers. And this is the confusion matrix which we got when we use the true values from these two studies. So if you use from Danforth et al., or if you use Voigt, which is a semi-auto. Okay, so now we have sort of true values. Okay, but what we found the accuracy is sort of, sorry, this is not visible, but the accuracy has reduced what we had for the simulated testing data set. So for the testing data set, we had like 93% accuracy, but this reduces to 85% accuracy when we are testing it for the real data set. So we do not understand why this was happening, because when we see it for the mock data set, which is basically creating same absorption line given the B and N parameters from those fittings. And we see that visually this seems to be very similar. So the brown one is the simulated and the black one is the real absorption line. And by visual thing and by chi-square fitting as well, we see that both of these simulated and the real data look similar. Then, but still, when we perform the classification algorithm for this mock data set, what we found is that the accuracy increased to like 95% accurate, which is 92 to 93% accurate, which is similar to what we have for the simulated data set. Two reasons which we could think why this is happening is because maybe, first of all, the true values which we are saying is again by a manual or semi-automated code. So maybe they are not as real as possible. Also, maybe the errors, the noise in the spectrum which we have added, we just add the pixel to pixel noise. But in the real data, maybe they are correlated. And therefore, we have this difference between the real and the simulated data set. But if we see the B and N distribution of this line, these lines, so we have the study by Danforth et al., we have the study by Vipers. So basically manual fitting, semi-automated code fitting. Then we have the fitting by this machine learning model. And then we have two other data sets which we created for the mock data set. And we see here that the distribution of P and N parameters is quite consistent with the other studies as well. So our model is performing well for the low redshift. This is like still an ongoing. So this part of work is published, and you can see more details about it in this paper. But it's a very long-term project, and we are now extending it to more complex lines, not just single and double lines, and also trying to incorporate that incorporate the fact that there could be correlated errors in the spectrum. But before I end this talk, this is the final slide of my talk. There could be failures. I mean, when we started this project, this is what we had for the column density and for the Doppler. You see the one-on-one line which we showed finally was not so one-on-one, and we see more bias at very low and high values. Two things which we found was why this was happening was, first of all, limited training data set. So we increased the number of training data set, but also the hyperparameters. So we were trying to make a model similar to what already has existed for other studies, but we soon realized that the hyperparameters has to be changed, and hyperparameters modifies a lot based on your science. So that's all for my talk. I will leave it to the summary slide. But before I do, I would also like to advertise myself. I have finished my, I will be finishing my postdoc position next year in 2025 August. And so I'm looking for another postdoc position. If you're offering one, come to know one, let me know. Thank you so much.
Thank you very much. Any question? Yes, Sean, please.
So what happens if you apply your algorithm to spectra different than those from HST? My own favorite spectrograph, take the spectrum with laser. So what happens?
Yeah, so if I do apply, so for the cases where the resolution element is very similar to HST, it gives reasonable results. But if I perform it on a very high resolution data or a very low resolution like SPSS or something like that, then it does not perform. So you can use this model and use another model called transfer learning, and you can sort of, as I said, you can extrapolate it to that resolution element. And this is one thing which we are also taking into account in our next part of the project, that it should be more generalized to all the spectrograph or line spread functions, as I said.
And another question. So as I understand, your code is able to classify either one line or two lines and then return the parameters of these lines. But the spectra you showed had like dozens of lines.
Yes.
So what do you do? How do you like do that in practice? Do you split the spectra in chunks or apply the algorithm?
So like in this case, we have the spectrum. So firstly, we divided them into chunks of, so like in this case, we divided them as 300, our input here in this case are like 301 pixels. And we divide them into chunks. So we divide them, we have a like chunk divider algorithm. And then so suppose in this case, you have a single line, but in this case, you have a, not Lyman-alpha. We have like a double line, and that once we have that, we input that to the chunk. Again, one more thing which I would like to mention here is that if I show a very high redshift quasar, sorry, like in this case, of course, it wouldn't be fair enough for this kind of spectrum. So that's why I said that this is for low resolution, where you can actually identify these chunks of 300. So yeah.
This work, I'm intrigued by the noise properties. So, the spectrum, the two data show is beautiful.
Yeah.
In reality, it's not like this. Right? So, what kind of instrumental effects, noise effects have you considered, and which you deliberately put it? Because it's not trivial.
Yeah. So what we have done is at each pixel we have added a Poissonian noise, but also we have added like a bias noise to that. So these are the two noises right now we have added, and as I said, because at each pixel we have added Poissonian noise, the error at one pixel is not related to the other pixel, but of course in real data it's not the case.
Also, you might have
calibration from exactly.
And then there are the lines from the atmosphere.
Yes. So we have not that taken.
That might not.
Explain
some of the drop of the.
Yes.
I do have more questions. And a question from Zoom. Thank you very much. Yeah, we can disconnect.